Last time we talked about marine and freshwater ecosystems, ocean productivity, both lentic and lotic water ecosystems, and zones of freshwater bodies. Today we're going to discuss food and agriculture. The first thing is global trends in food and hunger. Actually, most small scale farms have been replaced by these large industrial farms. And of course, that is really the case in the United States. What this means, though, is that the diversity of habitats, crops, and even genetic diversity has plummeted. And global food issues have been more to do with distribution than with the supply of the food itself. So it has more to do with getting the food to those communities that need it the most than having the food available in the first place. Food production has actually outpaced population growth due to some key technology fixes. We'll get to talk about one of those fixes in the coming slide, but population growth overall has increased by 1.7%, and contrast that with food growth, it's actually a greater percentage at 2.2. Okay, so what are these technology fixes? A lot of research and development has been dedicated to GMOs, or genetically modified organisms. What does this mean? It means it's an organism that has been subjected to some sort of genetic engineering. And genetic engineering mainly takes place through splicing a gene from one organism into the chromosome of another organism. So once we do this genetic engineering on an organism, it has been genetically modified, and we call it a GMO. These are organisms with entirely new genes sometimes, and even new organisms altogether. These are often called transgenic organisms. And it may surprise you to learn that most crops grown in the United States are actually GMOs. So we do this genetic manipulation primarily to increase crop yield. So specifically, some examples of this is the BT corn. You may have heard of this. They spliced in a gene from a bacillus species that is a poison to the pests that would feed upon this corn. So we call it BT corn. It's a GMO corn that produces proteins that are toxic to certain insects, pests, but importantly, that toxin is not at all going to affect humans, pets, livestock, or other animals. So we don't have the need for these chemical insecticides because the plant itself is producing the insecticide. Another example is the development of a rainbow papaya. That's the name given to a special transgenic papaya that was created to resist ring spot virus. And so what I would like you to do to learn more about why we need GMOs and what they do for us, I've posted this paper called Why We Need GMO Crops in Agriculture. And what I would like for you to do is read this paper. It's located in the week 6 folder. After reading it, write at least one paragraph that summarizes the main claim of this article, and then your reaction to the paper and its main claims. The writing that you produce through this reflection is going to be included in your Unit 2 reflection that is due on March the 10th. In addition, there's also a YouTube video for you to watch in the week 6 folder titled Are GMOs Good or Bad? Genetic Engineering and Our Food. So hopefully this video and the reading will do a good job in conveying to you that GMOs are actually not scary. We need them quite badly in order to make sure that we have enough crops and food to feed our global population. All right. So getting into the idea of food scarcity and malnutrition, food security is the ability to obtain sufficient, healthy food on a day-to-day basis. The reasons for the absence of food security across the globe and in the United States is a combined problem of economic, environmental, and social conditions. Many of us, unfortunately, even in the United States, live in what are called food deserts. And a food desert is typically an urban area in which it's difficult to buy affordable or good quality fresh food. There actually may be plenty of food, but none of it is nutritious. And online delivery does help, but often these services are prohibitively expensive. The most drastic side of the spectrum is famine. And famines are large-scale food shortages with widespread starvation, social disruption, and economic chaos. So there's a lot going on to produce the state of a famine in a country. It's often a combination of atmospheric and anthropogenic reasons, but it can also be precipitated by politics and war. And a great example, unfortunately, of a famine precipitated by political division is a famine that's currently ongoing in Yemen due to the Yemenian civil war that started in 2016 and is ongoing today. So these famines arise when there's political instability, there's war or conflict that displaces populations. Once those populations are displaced, it removes them from their farms or the ability to make their own food, either because they're physically removed or it's just too dangerous to carry on those practices of making their own food. Farming is highly time consumptive and requires intense attention. And as you can imagine, if there's war going on and you're constantly being displaced, you're not going to have that time to dedicate to farming practices. But even after better conditions return and you're in a state of peace and stability, it can often take a long time to recover because the people may have consumed all of the food that they need to pick back up those farming practices again. They may have had to exhaust their seed grain stores or eat their breeding livestock. If they didn't deplete their resources themselves, sometimes those resources are taken, stolen, eaten, shot, or poisoned. The subject of malnutrition is a serious one because the United Nations Food and Agriculture Organization estimates that nearly 3 billion people suffer from vitamin, mineral, or protein deficiencies. And that's because just consuming calories is not enough. Those calories that you choose to consume have to contain those key nutrients that we need to grow big and strong. And so calories does not necessarily mean nutrition. In fact, you can be obese and malnourished at the same time. So malnourishment is a general term for nutritional imbalances caused by lack of specific nutrients. Malnutrition can manifest in a number of different ways. There are several listed out here. We have quagmire, which is the lack of protein in children. This results in a lack of protein causing a bloating of the belly. It becomes distended and bloated and even discolors the skin. So we have an example here of what that would look like in a child. Another type of malnutrition is marasmus. This is a severe condition involving a lack of both protein and calories. And so a child that is suffering from this type of malnutrition is going to look thin and shriveled like this. An additional type of malnutrition that you might not be aware of is called goiter. And this is when the thyroid gland is enlarged and it actually causes, of course, trouble with eating and functioning normally with the thyroid gland. This is caused by a specific lack of iodine. We can go to the other end of the spectrum, which is obesity. Some 64% of Americans are overweight. That is up from 40% only a decade ago. Think about that. That is massive scales of obesity just here in the United States. About 1/3 of us are seriously overweight or obese. And obesity is more than 20% over the ideal weight for a person's height and sex. So there is a way to gauge whether you are at normal weight, if you're overweight, or if you are obese. We can take a look at the breakdown of obesity percentages across these different countries. And we can see through the different years here with purple being 2010 and blue being 1960, that just the United States here, we've shot up dramatically in the percentage of the population who suffers from obesity. This is in stark contrast to other countries like India, which suffer from being chronically underweight. Let's talk about food production. And globally, about 30% of all food that is produced is actually thrown away. In the United States, that percentage is even higher at 40%. That translates to over 1.3 billion tons of food that is thrown away. It's damaged in some way, either during transit or during storage. It can be used inefficiently or discarded after it's prepared. And even more food could be produced if large tracts of land weren't used for livestock and biofuels at the same time. And so we have the capability to convert even more land to increase our food production, but we already have consumed vast areas of land that can be cultivated for those agricultural needs. So this lowers the biodiversity overall and reduces or eliminates the ecological services that this land can provide, as we talked about in previous lectures. This land we convert for our resources do have natural ecosystem services that they provide to the ecosystem. And by converting it to agriculture, we strip away those services. So what do we eat on average? There are actually only a few edible plants and animals in the world that provide most of our food. And about a dozen types of grasses, 3 root crops, and 20 or so fruits and vegetables make up our diet. In addition to that, only 6 mammals are used, 2 domestic fowl, and a few fish species make up almost all of the food that we eat. So by and large, we don't really have a great diversity in the food that we consume on a day-to-day. Specifically in the United States, corn and soybeans have become our primary staple food. And in other countries, of course, rice and wheat are also important. We can take a look at the key global food sources by crop in the years 1990 and 2010 and see that they really just have increased in their use globally. If you're looking at these numbers and wondering why are soybeans and corn like so prevalent, and we might not eat soybeans and corn directly too frequently, but we have to consider that they're primary staples because they feed the livestock that is producing our beef. In addition to that, we often use their byproducts in other products like corn oil or corn sweeteners. So over time, food production and consumption has changed. And the global meat production has actually doubled within the last 45 years. That is an extremely drastic statistic. Meat and dairy consumption has quadrupled in the past 40 years. So just in the short amount of time, we've really done a lot to increase our consumption in meat and dairy products. Meat production is prized because of high calorie content and the abundance of protein, iron, fat, and other nutrients that are found within the meat. In addition to that, though, the production of livestock has increased. And this is due in part to the wide use of confined animal feeding operations, or CAFO. Another term for this is industrialized farming, where instead of having chickens just roaming around free range, they're packed inside facilities that look much like this, not really giving them a lot of space to live out their life. But really, that's not the point, right? We're trying to industrialize the farming process to increase the production of meat in this case. So as a result of the practice of industrial farming, soybean production has risen exponentially to keep up with cattle production. This is explicitly made clear in the case of Brazil. And here we have a graph showing cattle production and the area required to grow the soybeans to keep up with cattle production. And we see that production has increased dramatically from the year 1960 to current day. So it now takes 18 months to grow a steer to maturity. And surprisingly, you can make chickens go from a chicken into a nugget in just 8 weeks. So this really paints a picture that the energy investment in meat production is not solely tied to land clearing and development of land for the purposes of free range cattle or free range chicken. Instead, it's tied to agriculture that is used to feed that livestock. You can imagine the great amount of energy that is required to increase this production in the amount that we've seen over the past 40 years. And this actually translates directly into greenhouse gas emissions. Here we have the distribution of global greenhouse gas emissions by sector. We have a breakdown here with industry taking 21%, transport 14%, building 6%. Energy is the leader at 35%. But right up there with energy is agriculture, forestry, and other land use at 24%. So what this translates into is an increase in our greenhouse gases solely contributed by agriculture, forestry, and other land use. Here we have a plot going from 1970 to 2010 and the million metric tons of CO2 equivalents on the y-axis. You see clearly through time in this blue shaded area, we've increased the amount of CO2 that is being produced through agriculture alone. We also have increases in other key greenhouse gases. So this is directly tied to energy emissions associated with those industrial farming practices. But in addition to energy emissions, we also have non-energy emissions of greenhouse gases associated with agriculture. Specifically, that is the production of methane from cattle. Cattle cannot break down all of the compounds in the food that it eats. It relies on a specific type of microorganism called a methanogen to help break down that food so the cow can acquire nutrients within the food. But as a byproduct of that methanogenic activity, methane is produced. And that methane has to escape. It's a gas. It has to escape the cow. And so cows will burp out that methane and they'll also fart out the methane. And so this is a non-energy emission of a greenhouse gas. Methane is actually 20 times more powerful than carbon dioxide. So these are two key ways that agriculture and industrialized farming practices are directly contributing to increased greenhouse gas concentrations in our atmosphere. What about seafood? Regardless of whether it's farmed or wild, seafood requires wild source inputs. About 15% of all consumed animal protein is through seafood, and it's actually the primary protein source for over 1 billion people on Earth. What's drastic and we need to pay attention to is 13 out of 17 fisheries are now overfished to the point of being unsustainable. They are continuously being over harvested. And so what that does is it depletes the natural stocks of that fish community. If you don't leave enough for them to reproduce and create more fish, you're not going to be able to return to that fishery in the future to harvest fish. And so fish farms are beginning to increase in number, but we have to consider what they are eating. What are we feeding those fish farms? Of course, they are drawing from agriculture. So all of this is interconnected. And even though we are now instituting fish farm practices, it is still contributing to those energy emissions. So now let's go back to the idea of agriculture and what makes agriculture sustainable. We use soil and rely on soil for our agriculture, of course. Soil, by definition, is a mixture of sand, silt, clay, and organic material, and it is absolutely necessary for life to persist. Soil is formed by weathering processes that break down bedrock core stones into distinct layers. Through poor farming practices, we can actually convert this soil into unusable material. But before we talk about how each of these layers contribute to farming, let's talk about what they are. So the O layer is at the top here, just where roots are penetrating. This is the organic layer, and this is where we have the decomposition of leaves and other organic materials. Then we have the topsoil layer. This is the A layer, just a few centimeters into the subsurface. Here we have organic matter, organisms, roots, and inorganic minerals. Just beneath that, we have the E layer. This is the alluviated or washed out layer. This is where you will find clays, humic acids that are leached into lower levels. They originate here in the alluviated layer. And then just beneath E, you have B, which is the subsoil. And the subsoil is enriched in clays and other material that are leached from the upper layers here. So most food is actually grown in the A horizon. And in grasslands, the O and A horizons can actually be pretty thick, up to 6 feet or 2 meters thick. And so the conversion of grasslands into agricultural fields usually results in the erosion of much of the topsoil because you're continuously depleting these layers of their natural organic contents. Most other soils have an A horizon that is less than a meter thick. So those grassland horizons are really prime for agricultural uses. But contrast that with a different biome like a desert. These desert biomes may contain no A or O horizons at all because, again, these are mainly composed of organic materials and we don't have a lot of productivity in deserts. So let's talk about soil use and abuse. The use of nearly 2 billion hectares of agricultural land has led to massive amounts of soil degradation. And this is because areas that were never meant to be farmed were or are still being tilled to produce the next get rich quick crop. This can either be soybeans for feed for livestock or corn for biofuels. So all this does is degrade the soil without any efforts to replenish the health of the soil. And so this leads to erosion by wind and water. This direct degradation is going to facilitate increased degradation through natural processes like water outwash and aeolian processes like wind. You can also have indirect degradation through nutrient depletion, salt accumulation, acidification, and even pollution. So the misuse of this agricultural land leads to both direct and indirect degradation of the soil. The leading cause of soil loss overall is water. And that's because water is a great erosive force. Erosion is an important natural process that redistributes the products of geological weathering. But when you concentrate the powers of erosion through the direct degradation of that soil, it's going to basically overdo it. Erosion comes in many forms. You can have sheet erosion, which removes a thin layer of soil. You could have rill erosion, which occurs when small rivulets of running water cut small channels in the soil like this. In addition, you can have gully erosion, which is going to form bigger channels and even ravines, something that's depicted in the image behind this text here. And then finally, you can have stream bank erosion. That's also a problem in farmland streams where soil washes away from the banks of a stream. So that's water erosion. What about the other natural process of wind? Wind erosion removes plant cover and surface litter by agriculture or grazing, and the wind will lift the soil particles into the air and distribute them elsewhere. This is mainly a problem in areas where you have intensive farming, particularly of marginal lands. And in most extreme cases, you can have the effects of desertification. And that's where you just completely overuse the soil. You have no mitigating practices to replenish the nutrients in the soil, leaving it subjected to massive amounts of wind erosion and desiccation, drying up like this. In the last 50 years, 93,000 square kilometers have been lost in China due to the process of desertification. And in the United States, the Dust Bowl is still considered our country's greatest single ecological catastrophe in history. And that's because it not only had ecological effects, but it also left a massive chaotic economy for people to overcome during the Great Depression era. And so I'm going to show you a video that describes what this meant for communities that were experiencing the Dust Bowl.
During the 1930s, a terrible drought struck Texas and the Great Plains. This one was different from any drought in the past. It triggered a decade-long series of dust storms that became known as the Dust Bowl. The causes of the Dust Bowl were both natural and man-made. Lack of rainfall made the ground that grew wheat, corn, and other valuable crops parched and cracked. Over-farming and outdated agricultural techniques eroded the once fertile topsoil and depleted the ground of its nutrients. In Texas, many dust storms were mild, but there were a few severe ones called black blizzards. Picture a snowstorm, but instead of fluffy snow falling from the sky, imagine dark, choking dust swirling all around.
Dust storms bring darkness at noon.
The worst of these black blizzards struck with a vengeance on April 14, 1935. It is often called Black Sunday by survivors, and the Texas Panhandle was the hardest hit area of the state. The storm carried the dust and topsoil so far that ships anchored 300 miles off the coast reported finding dust on their decks. Newspapers from across the country feverishly reported about Black Sunday, including Associated Press reporter Robert Geiger, who was credited with coining the phrase the Dust Bowl. As he wrote, three little words, achingly familiar on a Western farmer's tongue, rule life today in the Dust Bowl of the continent: if it rains. While Texas and the Great Plains faced the Dust Bowl, the rest of the country sank into the Great Depression following the stock market crash of 1929. With the livelihoods of most Texans tied to farming and living off the land, the prices for any and all crops dropped severely due to the Depression. Sonora Babb, a California journalist originally from Kansas, returned home to visit her mother and could not believe what had become of the plains and its downtrodden people. She reflected, I saw them standing in line for the meat and potatoes of relief. Their stricken faces, one after another in the line, looked very much alike. As the soil that had once helped feed the nation turned to dust, many were forced to leave Texas in search of better farmland. Those who remained, however, received help from the federal government. The Civilian Conservation Corps was put in place to not only give people work, but also to try to conserve the soil and reverse the Dust Bowl. The CCC planted 200 million trees from Abilene, Texas, all the way to Canada. Another project called the Works Progress Administration, or WPA, employed millions of Texans on public projects. Most WPA jobs in Texas were in construction. Parks, swimming pools, bridges, highways were all built by hardworking Texans. Just as man-made and natural occurrences triggered the Dust Bowl, those same two forces helped end it. Rain began to fall more frequently, and the temperatures cooled. Farmers updated and changed their farming techniques to keep the topsoil healthy and fertile. The Dust Bowl taught Texans many important lessons about the land and how the health of it affects their society, economy, and community.
All right. So, what are the costs of agriculture? Well, one cost is water, mainly in the form of irrigation. That's something that is definitely required for agricultural practices, good or bad. You also need nutrients, mainly in the form of fertilizer. The addition of water and nutrients alters the water table and the composition of the soil. And fertilizers have created an agricultural boom, which is great for agriculture, but this has the cost of diminishing our natural areas. In the United States, the Ogallala Aquifer that stretches from South Dakota all the way down to New Mexico and Texas is predicted to dry up completely in the next 25 years. And over fertilizing the land creates problems, both in the terrestrial ecosystems, but also in aquatic ecosystems through a process called eutrophication, which we'll talk about in later lectures. But this is when the fertilizer that's used on land runs off into water bodies, including coastal areas. Another cost of agriculture is that it runs on oil. And the reliance on fossil fuels in America really began in the 1920s with the addition of tractors to agriculture. Energy use increased sharply after World War II with the invention of nitrogen fertilizer that was produced with natural gas. We also had increased reliance on diesel and gasoline in order to run our tractors, our combines, irrigation pumps, and other equipment, and that use has grown since then. So after crops leave the farm, there's actual additional energy involved in processing the food, distributing the food, and storing the food. And so the food system in the United States consumes about 16% of the total energy that we use. What's interesting to think about is that our foods require more energy to produce, process, and get to market than they actually yield when we eat them. Each hectare of corn produced in the United States consumes the equivalent of about 5 barrels of oil. That is quite a lot. It has been estimated that the average food item in the American diet travels 1,200 miles between the farm that it grew from and then the person that consumes it. So where else is this oil going to? About 1/3 of this energy is used in producing nitrogen fertilizers from natural gas. Another third is used for machinery and fuel. And then the final third is used for irrigation, synthetic herbicides, and other fertilizers. So for some foods, the processing, storage, and distribution is actually more energy consumptive than growing the crop itself. Another cost is the increased use of pesticides. Biological pests reduce crop yields and spoil as much as 1/2 of all of the crops harvested every year in some areas. And so, as you can imagine, with the advent of pesticides, this really gave farmers some sense of hope that they can increase their crop yields if they apply this pesticide to reduce the things that are eating their crops. The problem with this is that indiscriminate use of those pesticides are actually going to kill non-target species. That's a huge problem because it actually creates pests of organisms that were previously not a problem. And it also causes widespread pesticide resistance among some pest species. This is the same premise for the overuse of antimicrobial and antibacterial hand soaps and other products. By overexposing and having indiscriminate use of these products, we actually select for more hardy and robust organisms. So here's a map showing the usage of pesticides in the United States with warmer colors indicating a greater use of those pesticides. And you can actually see throughout the years that pesticide use for various food crops has grown from the year 1992 through 2012. So what can we do to kind of remove ourselves from those problems moving forward? A huge step in the right direction is moving towards sustainable farming. And that has soil conservation as an integral part of all agricultural practices. One practice is called contour plowing. And in contour plowing, you are plowing up across the hill rather than up or down. So you're following the natural contours of the landscape. And in that way, your conversion process isn't altering the land too much. Another thing is called strip farming. And this is the planting of different kinds of crops in alternating strips along the land to help conserve the soil. And a final way is called terracing. That is shaping the land to create level shelves to hold earth and water. So all of these are sustainable farming practices that are becoming increasingly popular as we make steps towards sustainable farming. Another thing that we could do is increase the amount of ground cover and reduce the tilling that we do in order to protect our soils. So annual row crops like beans or corn, they generally cause the highest erosion rates because they leave the soil bare for much of the year. And so often the easiest way to provide cover to the soil for protection is to leave the crop residues on the land after the harvest and just allow it to sit and cover the soil. And that way it's protecting the soil from the effects of wind and water. And it's also allowing the residual nutrients within that leftover crop to seep into the soil. Alternatively, instead of that method, you can also plant cover crops. These cover crops include things like rye, alfalfa, and clover, and they can actually be planted immediately after the harvest to help protect the soil, hold it in place, and provide nutrients to the soil. Another step in the right direction is low input sustainable agriculture. This can benefit both people and communities as well as the environment. This is in stark contrast to the industrialized practices that we've been talking about because we're taking steps towards having a more personable relationship with our farmers who are using agroecological farming and more natural practices. An example of this is the Minar family in Minnesota. So families like this that have family farms, they find that they can't compete with the big guys really, and sometimes they don't want to. So these folks are making money and staying in farming by returning to small scale, low input agriculture. So this farm is about 230 acres. They don't use any synthetic chemicals in their farming practices. They rotate their cows every day between 45 different pastures that they have. This is in order to reduce erosion and also maintain healthy grass for the cows. And then finally, they sparingly use antibiotics. They do use them in order to fight disease, but they're not used indiscriminately. The milk and the meat that they produce from their dairy cows are marketed through co-ops. And so if you're somebody who eats locally and perhaps knows a family farm and buys things at your local farmer's market, for example, you might be a locavore. A locavore is someone who consumes only locally produced food. This has the benefit of supporting local farmers, and it also helps grow the local economy and ensures that you are being provided fresh and healthy food. This can help maintain a viable farm economy in small communities. It could also help slow the conversion of farmland into expanding suburban subdivisions. And farmers markets are usually the easiest way to eat locally. If you have a local food co-op, that's another great way. There's one that's in the north part of Knoxville called Three Rivers. And finally, just give it a try. Eat more sustainably grown fruits and vegetables. They're better for you and they often taste better too. So to conclude, food production has grown faster than the human population in recent decades, and the percentage of people facing chronic hunger has actually declined. There's increases in food production that mainly result from research and development of new agricultural technologies, including GMOs. And these changes bring about environmental problems, of course, including soil erosion and water contamination from pesticides and fertilizer. And then finally, consumers can influence farm production by choosing what food they buy and where they buy it.